Okay, so this is another video on electrolysis. So again, it's only relevant to paper 1. In the previous videos, we've looked at how the ions are separated, but we haven't looked at what happens to the ions after they are separated and how they end up back at the metal and the non-metals. That's what we're going to look at in this video. So I started off with a typical ionic reaction. I've got sodium reacting with chlorine. Sodium is my group 1 metal, it loses 1 electron. Chlorine is my group 7 non-metal, and it gains 1 electron to have a full outer shell. On the left hand side, I'm calling sodium and chlorine atoms because they've got all of their electrons. On the right hand side, I'm now calling them ions because sodium is lost and chlorine has gained an electron. You'll also see that as ions, they have charges. Sodium has lost an electron and is positive. Chlorine has gained an electron and is negative. And we looked at the use of electrolysis to separate these ions. So we connect our electrodes to a battery, one to a positive end, one to a negative end. We insert those electrodes into a liquid form of our ionic compound. When we turn that battery on, the positive sodium ions will all move to the negative cathode, and the negative chloride ions will all move to the positive anode. So we've looked at how we can use electrolysis to separate the ions, but we haven't looked at what happens next. We haven't looked at how we go from having that sodium ion to getting back to the sodium atom. So essentially what we're going to be doing is we're going to be working backwards from this process here. It started out with the sodium atom. Sodium lost an electron and then became a sodium ion, which is what I've got here in my electrolysis experiments. I want to use electrolysis to split up my ionic compound and get my original metal back and my original non-metal back. In order to get my original metal back, I'm going to need to go from my sodium ion back to my sodium atom. And we can write an equation to represent this process. So we've already seen that at the cathode, the product is going to be sodium, but we didn't show exactly how that would happen. So at the moment, at the cathode, we had got an Na plus ion, and we want to get back to just normal sodium, a sodium atom. That's what we're trying to get back to, a normal just sodium atom with all of its electrons. Okay? In order to form the sodium ion, sodium lost 1 electron. That's why it's got a positive charge, because it had lost 1 electron. If I want to reverse that process, then what I need to do is give sodium its electron back. If I give sodium back its electron, it ends up just being a neutral sodium atom again. If I had a different metal in my electrolysis experiment, let's say, for example, I had calcium. Calcium is in group 2. It loses 2 electrons when it reacts. So if I've got calcium, it would have a +2 charge on it. If I wanted to take my calcium ion and convert it back into a calcium atom, because it's +2, it had lost 2 electrons. I then need to give it those 2 electrons back, and then back to calcium again. If I had aluminium, it's a group 3 metal. It would have a +3 charge after it's reacted. If I want to take my aluminium ion and get back to aluminium, well, it lost 3 electrons. I need to give it 3 electrons back, and now I'm back to aluminium. Your metals are always going to be positively charged. They've always lost electrons in the reaction. To get them back to the atoms, you need to give them those electrons back. If they're +1, give it 1 electron back. +2, give it 2 electrons back. +3, give it 3 electrons. And then you end up back at the neutral atom. You end up back at the element that you started with. The other product we saw form at the cathode was hydrogen. If you remember, when you electrolyze something aqueous, you typically form hydrogen at the cathode. And we saw hydrogen was H+. Okay, it was H+ because it had lost an electron. So again, you would need to give it the electron back, and when you do, you would form hydrogen. However, hydrogen as an element does not exist as a single hydrogen atom. Hydrogen is diatomic and it always exists as H2. When you form hydrogen as an element, you are not going to form it as H, you are going to form it as H2. Because I've got two hydrogens on the right-hand side, then I need two hydrogens on the left-hand side. So I need to balance this equation. When I'm balancing an equation, I never use small numbers, I always use large numbers, and I put them at the front. So if I've got two hydrogens on the right-hand side, and I need two hydrogens on the left, I would have to put a big 2 in front of that hydrogen so that it was balanced, so that I had two hydrogens on each side. If I've got two hydrogen ions, they will each need to gain one electron to form H2, which means in total, I'm going to need 2 electrons. I'm just going to draw this particular one underneath so you can see what I've got. So hydrogen only has 1 electron. If it's H+, it's lost the only electron it has, and it actually just has an empty shell. I've got 2 H+, so I'm going to draw 2 separate hydrogen ions. I'm going to give each of these hydrogen ions 1 electron. So I'm going to go plus 1 electron, plus 1 electron. So they're each going to get 1 electron. And when that happens, I end up with my hydrogen atoms. Okay? But individual hydrogen atoms are unstable. Okay? Their outer shell is the first shell. The first shell can hold 2 electrons and they've only got 1. So what will happen is these 2 hydrogens will pair up and it will form H2, because in H2 each hydrogen has 2 electrons in the outer shell, so each hydrogen is happy. So what's happening is you've got 2 separate hydrogen ions, they each gain an electron to form the hydrogen atoms, which will then immediately pair up to form H2. The reason they pair up is hydrogen atoms are unstable. They've got 1 electron in their outer shell, they want to have 2. By pairing up, each hydrogen ends up with 2 electrons in their outer shell, so they are happier paired up than they were separately. Remember, the reason hydrogen only wants 2 electrons in the outer shell is because its outer shell is the very first shell, and the first shell can only hold 2. So this is how we represent this equation. And you'll notice as well the difference between the big numbers and the small number. When I had a big number, I drew 2 totally separate hydrogen ions. They were not bonded together. But when I had my small number, H2, I had my 2 hydrogens actually bonded together. So this is my H2, and then over here, my 2H+ would be separate. Okay, so what you'll notice is it's obviously, this is all at the cathode, so the positive ions always go to the negative cathode, and when the positive ions get to the cathode, they gain electrons, and then they end up being neutral. Because you are always gaining electrons at the cathode, so you gain electrons, we can say that reduction occurs at the cathode. Reduction. Okay, so oil rig, oxidation is loss, reduction is gain of electrons. You always gain electrons at the cathode, so reduction takes place at the cathode. We'll now have a look at the anode. Okay, so at the anode, you're going to have your negative non-metal ions. And we saw in the previous video that the product at the anode in this case is going to be chlorine. But again, we didn't look at exactly how that would happen. So just like with sodium, I'm going to write a half equation for chlorine. Okay, chlorine is starting out as being Cl minus, and I want to convert it back into Cl, right? So if I look up here what I had before, Cl minus, I want to get it back to Cl. Well, how did it become Cl minus in the first place? It became Cl minus because it gained an electron. So if I want to get it back to where I started, then I'm going to need to take that electron away. I take that electron away and I get back to Cl. However, just like with hydrogen, when chlorine is an element, it never exists as a single Cl atom. It actually exists as Cl2. Okay, so in this reaction up here, I haven't drawn two separate chlorines, but as an element, chlorine is always going to be Cl2. So I'm not just going to form Cl, I'm going to form Cl2. Okay, and again, like we had with the hydrogen equation, I need to balance this. If I've got two chlorines on the right, I'm going to need two chlorines on the left. And to balance, I use a large number and I put it at the front. Each of these chlorines will need to lose one electron. So in total, I'm losing 2 electrons to form my chlorine. I'm going to draw this one for you as well. I'm starting off with 2 Cl minus. Again, the big 2 tells me that these Cl minuses are totally separate. So if it's Cl minus, it's got the 7 electrons that a chlorine would always have, being in group 7, but an extra electron because it's got a negative charge. Remember, negative means it's gained an electron. So there's 1 Cl minus, and underneath it, I'm going to draw another Cl minus. 2 separate Cl minus, okay? And what's going to happen is each of those Cl minus is going to lose the electron. Remember, minus means they've gained an electron. They lose that electron, and you're going to end up with your neutral chlorine atom again. So a neutral chlorine atom just has 7 electrons. It wants to have 8 electrons. So rather than 2 chlorines existing by themselves, both of them unhappy with unfull outer shells, what's going to happen is these chlorine atoms will pair up and they will form Cl2. And the reason they pair up is when they share their electrons, they both end up with a full outer shell. So you've 2 separate chlorine ions, they each lose an electron, they form those chlorine atoms. Those atoms will pair up to form a Cl2 molecule. Okay, so that's what's happening here. It's the same equation for all of the halogens. Remember, we typically get halogens formed at the anode, and your halogen equations are all going to be the same. So if, for example, I had bromine instead as my halogen, bromine's in group 7, it also has a -1 charge. I want to get bromine back to my bromine atom, but because it's a halogen, it's going to be exactly the same as chlorine, and it's also going to be diatomic. That means if I've got 2 of them on the right, I need 2 of them on the left. 2 bromine ions, they each need to lose an electron, so in total, I'm losing 2 electrons to form Br2. Okay, so these are called half equations. At the cathode, we saw we were always gaining electrons. At the anode, we are always losing electrons. So you're always going to lose electrons at the anode. And if you're losing electrons, it is oxidation that occurs at the anode. So hopefully you remember oil rig. Oxidation is loss, reduction is gain of electrons. You're losing electrons at the anode, so it's oxidation that is taking place at the anode. There's just one common mistake that I often see when I'm marking half equations, and again, I just want to show you why it's wrong to hopefully help you avoid this mistake. So we've just seen that the halogen equation, 2 Cl minus 2 electrons going to Cl2. And often what students do is they might write a Cl minus and they might use a small 2 there instead. And they'll write something that looks like this. And they'll be confused when they get it wrong. If you're using a small number, it means that they're actually bonded together. So it's fine to use it over here. That Cl2 would represent the 2 chlorine atoms bonded together to form a Cl2 molecule, both atoms ending up with a full outer shell, both atoms ending up happy. If you use a small 2 over here, that would suggest that your 2 Cl minuses are bonded to each other. Okay, and that's not going to happen for 2 reasons. Number 1, If they're both negatively charged, if these ions are both negatively charged, then they're going to repel each other because the same charges will repel. So they're not going to come together and form a bond. Number 2, if I actually draw one of those chlorine ions, remember chlorine has got 7 in its outer shell, but it's Cl minus, which means it's gained an electron. So your chlorine ion, your chloride ion, already has 8 electrons. It doesn't need to form a bond to have a full outer shell. So your Cl minus is not going to form another bond, so it's never going to be Cl with a little 2. Remember, the small 2's mean they're actually bonded together, but when I use that big 2 at the front, it means I've got 2 separate chloride ions. So I would have 1, 2, 2 totally separate chloride ions, and that's okay. But using the small 2 means they're bonded together. That wouldn't happen. They'll repel each other because of the same charges. They don't need to bond because they've got a full outer shell. So make sure that you know how to use these numbers correctly. Okay. The other thing that you may see is instead of writing the equation like this, what they'll often do is they'll move the electrons to the other side of the arrow. So they'll keep the 2 Cl minus over here, and they'll keep the Cl2 over here, but they'll bring the electrons to the other side of the arrow. And just like in maths, if you bring it to the other side of the arrow, you're going to change the signs. You're going to end up with plus 2 electrons. So it'll be 2 Cl minus, arrow, Cl2 plus 2 electrons. Now this is exactly the same. They've just moved the electrons to the other side. But what sometimes catches students out is now you've got a plus 2 electrons. And then they're going to ask you, is this oxidation or is this reduction? And you see that plus electrons and you think, oh, the electrons are being gained, therefore it's reduction, okay? But it's not, all right? Cl2 would have to gain electrons to become 2Cl minus, but you're not being asked about the Cl2, you're being asked about the 2Cl minus, okay? And the 2Cl minus would need to lose electrons to become Cl2. So my general advice is, if it is negatively charged, if the ion is negatively charged, then it is always going to be oxidation. Always, always, always. Because if it's negative, it means that it has gained an electron, and then it must lose an electron in order to become neutral again. If it needs to lose an electron, then it needs to be oxidized. So if you've got a negative ion, it's always going to be oxidation that needs to occur. If you have a positive ion, that means it's lost an electron. It needs to gain one to be neutral again. So reduction has to occur. So don't get put off by the signs in front of the electrons. If it's negative, oxidation needs to occur. If it's positive, reduction needs to occur. I'm going to get you to do some questions for me. You can start with question number 8. So for these half equations, I've started by filling in some of it for you and then asking you to complete it. And then the questions below, I've asked you to just write the half equations yourself. I will tell you that calcium is in group 2. So that should tell you what charge calcium has. Potassium is in group 1 and lithium is in group 1. So use that information to figure out what charge they will have and then write the half equation. The following metal ions, again, I'll tell you what groups they're in case you don't have the periodic table to hand. Chlorine is group 7, oxygen is in group 6, fluorine is 7, bromine is 7, and nitrogen is 5. So knowing what group numbers they are, that should tell you what charges they have. And then you can again use that information to complete these half equations below. Just trying to make this slightly bigger. So complete from number 8 down to number 21, and then press play when you're ready to see the answers to those questions. Okay, so I filled in the answers. First one, sodium +1. So give it an electron back. Mg +2, it's lost 2 electrons, give it 2 electrons back. Iron's lost 2 electrons, give it 2 back. Aluminium's lost 3, give it 3 back. Potassium's lost 1, give it 1 back. Copper's lost 2, give it 2 back. Iron's lost 3, give it 3 back. Okay, you should have an ion on the left give it back the electrons, and you're going to form something neutral on the right. The half equation for calcium, it's in group 2, so it's got a +2 charge. Give it back 2 electrons, and it becomes neutral calcium again. Potassium, in group 1, +1 charge. Give it back an electron, and it's potassium. Lithium, give it back an electron, and it's lithium. So ions are on the left. You're starting with the ion. You give the metal ion back the electrons it lost, and it becomes an atom again. They're the metal half equations. Metals are always positively charged, so you give them electrons back. Non-metals always gain electrons and become negatively charged. If they're in group 7, they'll gain 1 and be -1. If they're in group 6, they'll gain 2 electrons and be -2. If they're in group 5, they'll gain 3 electrons and be -3. Because they're all negatively charged, they will all move to the positive anode. The reason, because opposite charges attract. At the anode, they can then lose those extra electrons that they've gained, and that allows them to become atoms again. But what we saw with the halogens is that instead of becoming just single atoms, they do become diatomic molecules. So your half equations must reflect that. Sorry, I realise that's probably quite hard to see. I've got F minus going to F2. I need to balance this equation, so I use a large number to balance the equation. I've got 2 F minus. Each of them have gained an electron, so I take those 2 electrons away. Then all of these halogen equations are exactly the same. What is oxidation? It's the loss of electrons, and electrons are lost at the anode. Reduction is the gain of electrons. Reduction takes place at the cathode. I'm going to go through the next questions with you. Identify whether oxidation or reduction is taking place. So you can see that calcium, the Ca2+, is gaining electrons, therefore it must be reduction, and this process is going to happen at the cathode. Up here, again, I've got aluminium. I've got a positive ion, aluminium. It's gaining electrons, so it is going to be reduction. That's also going to take place at the cathode. Here I can see bromine is losing electrons. That's oxidation. That's going to take place at the anode. This is one of those equations I was talking about. Okay, they've moved the electrons to the other side, and now you're going to see this plus electrons, and you might think, oh, gaining electrons, it's reduction. Okay, but it's not. If you're starting out with a negative ion, it's always going to be oxidation. So 2Cl minus, what I've got on the left is what I'm looking at. It's negatively charged, it's going to be oxidized. Fluorine, again, negatively charged, it's going to be oxidized. Potassium, positively charged, it's going to be reduced. So with the potassium, you can easily see that it's gaining their electron, so it's obvious that it's being reduced. I appreciate that here it's slightly harder to see, which is why I usually write the electrons on the other side, and then you can clearly see that they are losing electrons. But general rule, if you're starting with a positive ion, it's going to be reduction. That happens at the cathode. If you start with a negative ion, it's going to be oxidation, and that is going to happen at the anode.